things to look at. So first of all, looking at the week ahead, I think everybody is kind of on the same page with that. The big things due this week are, you've got a post-lecture that is due tomorrow in Smart Work. So that is that's this one right here. I can see a good number of you already did it, probably because I didn't change the due date from last night till Tuesday until just about a minute ago. But that's due tonight, or tomorrow night rather. The Chapter 8 homework is due on Wednesday night, as is the Chapter 8 quiz. So our focus today is on reviewing Chapter 8 and getting ready for that Chapter 8 quiz. I just took a peek at our syllabus to make sure that I had the deadlines right. So solubility rules was due last night for 100%. Those of you that did not pass it by last night, you still got 2 more weeks to get that one figured out for 3/4 credit. On that same day, you'll see that that is when the bonus deadline for the equation balancing will be due. So again, I've said this for the past couple of sessions, it's worth reiterating. If you've passed solubility already, equation balancing is the last hurdle on the track. And you've got some time and you've got all the resources, you've got all the tools. We've covered everything on that proficiency. It's worth your while to go after it, especially given the fact, and I mentioned this on Friday, especially given the fact that you do not need to know how to balance redox reactions. Yes, there's a redox equation on there, but you can technically get it wrong and get everything else right and still pass the proficiency. It's an important piece. Now, that's not going to absolve you from needing to know how to do it on exam 3, but it is an important piece nonetheless. So keep that in mind, keep that in your head as we're kind of moving forward. As far as the quiz is concerned, let's go ahead and do a little bit of a breakdown here. The quiz itself has 6 questions. One of those questions is a solution concentration kind of question. So that kind of question would be, can you determine molarity or percent from raw data? So if I tell you that I've got 39.1 grams of potassium hydroxide in 100 milliliters of water, can you tell me the molarity? Can you tell me the percent by mass if I give you 50 grams of sodium chloride and 150 grams of water? That's what one of the questions will be about. Another concentration question that is on there is a conversion question. You'll either be asked to convert from percent to molarity or from molarity to percent. And certainly we can do some examples of that today. It's not something that we talked about specifically. We kind of ate around the edges of it with some of our examples. We did parts per million to molarity. We did molarity to parts per million. We didn't quite do all of it, but we can work our way through it. This one we did not talk about explicitly. It was in the reading. It was part of one of the post lectures. The Bronsted-Lowry definitions of acids and bases. So in this particular question, you're going to be given a chemical equation. You're going to need to identify the acid and the base in that equation. The setup is actually really simple. In acids, we are looking for things that are proton H plus donors. That is, they're going to give away an H plus ion. In bases, we're looking for proton acceptors. They are going to be things that take that H plus ion. And so the easiest way to do it is, we talked about this in terms of redox reactions, finding those matched pairs. Look at the matched pairs and see how they are different from each other. So NH3 turns into NH4 plus. That's a matched pair. And we can see that the difference between them is that the NH3 added an H plus. Well, by that definition, it accepted a proton. It's a proton acceptor. NH3 ammonia is a base in that situation. The fourth question is a titration calculation of some kind. And then the last two questions concern a redox reaction where you have to identify oxidation, reduction, oxidizing agent, and reducing agent. Now, I think the important things out of this that we can draw, and they are significant, there's no solution stoichiometry. Calculation that you have to do with a chemical reaction is a titration. You can use the titration equation for it. There is no net ionic equation. There is no redox balancing. Now, that's not to say that those three concepts aren't important. You're going to find them on exam 3. But what that is to say is that you're not going to be tested on those over on this quiz. We kind of came to a conclusion that those three concepts in particular are kind of on the more difficult side. It'd be nice if you had a little bit more time with them. And so looking ahead, 2 weeks from now is our third exam, 2 weeks from today, actually. That's the appropriate time to test those concepts. You'll have more time to do them. So those don't go away, but we're postponing them for a while. So that's our breakdown for the quiz itself. There will be 6 questions. Those are the 6 questions that you need to know how to do. You'll have 40 minutes in which to do it. And the equation sheet and the periodic table have been preloaded into the quiz. You shouldn't have any problems with accessing those right away. There are no take a picture kinds of questions, so you don't have to worry about any of that kind of stuff. Any questions about this breakdown? Okay, so with this information in hand, and based on some of the things that you looked at over the weekend, we've got about 35 minutes. What do we want to talk about? I'm going to turn the review back over to you. What are some things that we need to talk about? What are some things that you want to review out of this chapter?
Can we talk about the number 2, so like concentration conversion, so percent to mole?
Okay, I kind of anticipated this would be one of the ones that we did because we didn't talk about it exclusively. But yeah, let's go ahead and do that. So the real trick into these, let's just kind of pick one out of the air. A relevant question based on the lab that we did last week. Convert 5% acetic acid into molarity. Now, the trick to this kind of question is understanding what your definitions are. Because if you can understand the definitions, it can take you pretty far. In 5% acetic acid, we have 5.0 grams of acetic acid, HC2H3O2, for every 100 grams of solution. What we're trying to convert it to is molarity, which would be moles of acetic acid per liter of solution. So you can notice that if we go across the top, all we need to do is convert our grams into moles. The unit, as far as the substance is concerned, is exactly the same. And the same thing in the denominator. We need to turn those grams into liters because the unit, as far as the substance is concerned, is the same there as well. Well, turning 5 grams into moles is no big deal. We've done that kind of calculation since, mid-September. What piece of information are we missing to turn the grams of solution into a volume? Density, exactly. In density, I would have grams of solution divided by milliliters of solution. Now, let's just say that for the purposes of this problem, the density is pretty close to 1.05. If we put that into action, that means that we have 100 grams of solution. And we're told that for every 1.05 grams of that solution, we would get 1 milliliter. And then there are 1,000 milliliters in 1 liter. The end result would be 100 divided by 1.05 divided by 1,000 to 3 significant figures. We would be talking about 0.0952 liters, 95.2 milliliters for this particular solution. Now in the numerator, we had 5.0 grams of acetic acid. To turn that into moles, we need a molar mass. Hydrogen is 1.01. Carbon is 12.01 times 2 of them. Hydrogen is 1.01 times 3. And oxygen is 16 times 2. So we've got 60.06 grams of acetic acid in 1 mole. Five divided by 60.06 gives me 0.083 moles of acetic acid. And so now if we put that all together, we have 0.083 moles of acetic acid divided by 0.0952 liters of solution. 0.083 divided by 0.0952 would give us a concentration of, to 2 significant figures, 0.87 molar acetic acid. Given the context of your titration, this number should make a good bit of sense. If the acetic acid if the vinegar solution that you had was 5%, and you had 5 milliliters of it, and you're titrating it with 1 molar sodium hydroxide, it should take a little less than 5 milliliters to finish the titration, which in most of your cases was exactly what you saw. So from a breakdown standpoint, this was one way to do that. Now, as you can see, everything we did from a calculation standpoint all involved dimensional analysis of some degree. Well, what that means is that we could have put those steps together into one long calculation string as well. So if we had done that, I had 5.0 grams of acetic acid for every 100 grams of solution. .06 grams of acetic acid in 1 mole. That would have got rid of my grams. 1.05 grams of solution for every milliliter of solution. 1,000 milliliters in a liter. If I put that string in, 5 times 1.05 times 1,000 divided by 100 divided by 60.06, I would have got the same 0.87 molar acetic acid. So either way you look at it, yes, you will need a density. And yes, a density will be provided. But whether you choose to approach it from this dimensional analysis standpoint or breaking it down into pieces and parts, you'll end up in the same location. You just have to remember your definitions. So again, it comes back to, do you understand what these two terms mean? Do you understand what percent is? Parts of 100. X number of grams divided by 100 grams of solution. Do you understand what density is? Can't tell you the number of times that people will take this density and apply it only to the acetic acid. When it should belong to the solution. So these are the little things to kind of keep in mind. And again, it doesn't matter how you break it down, you're going to end up in the same place either way. You want to do an example going the opposite direction just for completion? Just for completeness? All right. Convert 1.11 molar potassium hydroxide 2% if the density is 1.09 grams per milliliter. Once again, it is important that we understand and that we know our definitions. What does 1.11 molar mean? It means I have 1.11 moles of potassium hydroxide for every liter of solution. And where am I trying to go? I'm trying to go to grams of potassium hydroxide per 100 grams of solution. Now, if that's not possible to get to by dimensional analysis, one thing I can do instead is, let's say that I don't want to go through the rigors of trying to figure out what 100 grams looks like. What I can do instead is this. I can take those grams of KOH divided by grams of solution and multiply it by 100%. That's well within my realm of possibility. And in this case, that is actually going to be the easier course of action, because how I get that denominator to 100 would be really difficult to do. But I can figure out grams of potassium hydroxide, grams of solution, divide them, and then multiply that ratio by 100. So to get from here to here, I need a simple conversion using the molecular weight. For here, again, a relatively simple conversion using the density. This is one that we could do via dimensional analysis or by breaking apart. It really doesn't matter. Again, I'll show you both ways. You can kind of make your own decision from there. 1.11 moles of potassium hydroxide. Every mole of potassium hydroxide, potassium 39.09, 39.10 rather, plus oxygen 16, plus 1.01 for hydrogen, 56.11 grams of KOH. 1.11 times 56.11 is 62.3 grams of potassium hydroxide. Second task, I have 1 liter of solution. Every liter has 1,000 milliliters, and every milliliter weighs 1.09 grams. So, little quick math there, that's 1,090 grams of solution. Since I now have both of these, I can plug them into the equation. 62.3 grams of KOH divided by 1,090 grams of solution times 100%. 62.3 divided by 1,090 times 100. 3 significant figures, it would be 5.72% KOH. If I wanted to go the dimensional analysis route, I could. Again, all the steps here are all kind of following the same pattern. 1 mole of KOH is 56.11 grams of KOH. My moles cancel. 1 liter is 1,000 milliliters. 1 milliliter of solution weighs 1.09 grams. So my liters are gone, my milliliters are gone. I do the calculation, 1.11 times 56.11 divided by 1,000 divided by 1.09. I would get 0.057, 1 in this case. That would be grams of KOH per gram of solution. And so that's where I would have to multiply by 100 to get 5.71% KOH. So you can do the dimensional analysis route. You just have to remember that that's the mass ratio. You'd have to multiply it by 100 at the end. regardless of how you approach it, again, the process is the same here. You can break it up into pieces, or you can use dimensional analysis. The results you get are within error of each other. Usually, plus or minus 1 on that last significant figure. And the way that I've programmed the the Blackboard, it should accept either one is fine. All right, any questions about this? All right, what else do we want to talk about and go over? So let me bring up that big master list again. So we've hit this one pretty hard. A redox equation? Okay. So again, for the redox equations, it's going to look something like this. Now, on the Blackboard quiz, this is broken up into 2 parts. Part 1 is the element reduced and the element oxidized. Part 2 is the oxidizing agent and the reducing agent. But it's all talking about the same equation. So keep that in mind. Let's put in a reaction here. Chloride reacts with permanganate ion to make chlorine and manganese 2. Now, we're not being asked to fill out all the rest of this in terms of, where the waters are, where the acid protons are, all that. Just from a pure standpoint of recognizing that this is an oxidation reduction reaction, what is actually changing? What's happening in this reaction? Now, unfortunately for some of you, this means that we have to go to oxidation numbers. And so you cannot solve this without oxidation numbers. It's impossible to do so. For oxidation numbers, again, we have to go to our rules. So if you remember our rules for oxidation numbers, they are basically summarized in 2 ideas. Sum of the oxidation numbers in a given substance is equal to the charge on that substance. And then there are 3 elements whose oxidation numbers are generally well known: fluorine, oxygen, and hydrogen. So with those in mind, I look at the chloride ion here. It's the only element in this. It's got a -1 charge, so its oxidation number has to be -1. I look at the permanganate ion here. I've got manganese and 4 oxygen atoms, equaling out to a total charge of -1. Well, if I do a little bit of quick algebra, each oxygen, based on rule 2, has to be -2. So I've got manganese plus -8 is equal to -1. Manganese must be +7. So I've got a +7 for the manganese. I've got a -2 for the oxygen. The chlorine here. The chlorine has no charge. It's the only element in the substance. And so it must have an oxidation number of 0. It's got no charge. There's no charge to be had on it. Its oxidation number has to match the charge. And the same thing for the manganese ion here. Manganese 2 ion, it's going to have a +2 charge because, well, it's the only element and that's the only charge. So we need to look at what's changing. And again, this is where we come to that idea of matched pairs. There are two substances in this equation that look similar. The chlorine and the chloride. And there's another matched pair here, the permanganate and the manganese. Both contain manganese. In those two compounds, we see that there are some changes. We see that the chlorine has gone from -1 to 0. And the manganese has gone from +7 to +2. Now, based on our definitions, how would we describe what happened to the chlorine? Is this oxidation or is this reduction in the chlorine, or excuse me, the chloride? Okay, how do you know that it's oxidation? It's losing electrons. So this process is oxidation, if I can spell. Okay, remember, there are two ways of going about identifying. There's the Leoger, there's the oil rig. Both of them say the exact same thing. Loss of electrons is oxidation. Oxidation is loss of electrons. Remember those mnemonic devices in that post lecture that I gave you. Now, the other way that we can look at it is that oxidation is a gain of positivity or a loss of negativity. When we lose electrons, our oxidation number is either going to get more negative or less positive, depending upon, wait, strike that, reverse it. In oxidation, we are losing electrons, so we're either going to get less negative or more positive. Now, in the case of the chlorine, we're going to see here we got less negative. That's oxidation. Reduction, on the other hand, that's what's happening to the manganese. We're seeing a gain of negative charge or a loss of positive charge. In this case, we are talking about a loss of positive. We're going from 7+ to 2+. So we really don't think about that as gaining negative, even though that's what's happening. We are seeing a reduction in our positivity, though. So to answer the first two questions, the element oxidized and the element reduced, we would say chlorine is oxidized and manganese is reduced. Because again, we're asking for elements here, not compounds, not ions, elements. And the element that is changing is the chlorine, is the manganese. So that would be one of those questions. The second of those questions would be, what is the oxidizing agent? What is the reducing agent? Now here, we're not interested in the element itself. We're interested in the entire reacting species. So the chlorine was oxidized. What is the reducing agent then? The reducing agent contains the element that was oxidized. So what reacting species contains the chlorine? Right, the chloride ion. The chloride ion is my reducing agent. Again, if I say chlorine here, that is incorrect. Elemental atomic chlorine is not part of the reaction, but the chloride ion is. And the chloride ion is what ends up being the reducing agent. What's my oxidizing agent? What reacting species contains that manganese? It'd be the permanganate ion. Again, not the manganese. It's the whole thing, the permanganate ion. I've got to hammer that into you, because if you give me an incomplete answer there, I have to mark it wrong because it's incorrect. So just simply saying manganese there is incorrect. Manganese is not a reactant, but the permanganate ion is. Oxidizing agents and reducing agents are only found on this half of the reaction. Nothing from the products, just reactants. All right, we've got time for one more question. I'm going to be the one who selects it. This speaks to that Bronsted-Lowry definition thing I was talking about before. If I gave you something like this, CH3NH2, methylamine, reacts with hydrofluoric acid, HF, to make methylammonium ion and fluoride ion. You need to be able to identify the acid and the base in this reaction. Now, under the definitions that we gave you for identifying acids and bases in solubility, those were easy to pick out. You looked for the hydrogen, you looked for the hydroxide. In the Bronsted definition, it's not quite that simple, but you should be able to do the same thing that we did with redox reactions in terms of finding matched pairs. The HF and the F minus are a matched pair. The two organic compounds are a matched pair. What you want to look at is what are the differences between them. This one seems to be plus an H plus. This one seems to be missing an H plus. How does that fit into those definitions? Remember, acids give away H pluses. Bases add H plus ions. So under this definition, what is my acid? It's the HF, it's the hydrofluoric acid. And what's my base? And this one, the methylamine. Reason I want to caution you on this is because in some of these scenarios, what you'll end up finding is water has the capability of acting as an acid or as a base depending upon its situation. So we can see water adding an H plus and becoming the hydronium ion, H3O plus. We can also see water ditching a hydrogen and becoming hydroxide ion. It has the capability of acting as both. It's a property of water known as amphoterism. More about that on another day. But don't get caught into the trap of thinking of water as this purely neutral kind of environment. It actually can kind of go both ways based upon what it's around. So keep that in mind. Don't let that trip you up on the quiz. I'll see you on Wednesday.